The next example of feature engineering that I'm going to be talking about is from a social media site called TV Tropes. If you haven't used TV Tropes before, you may want to take a second here, pause the video, and check it out. That may be a better way of understanding what the thing is than me trying to explain it. But I'll try to do that anyway. So first, it's a social media site, and it has a bunch of tropes. So tropes are themes that reoccur in popular media. So one example of a trope is the absent-minded professor trope. What TV Tropes does is it makes a catalog of all of the examples of a given trope across a variety of media: television, film, books. So here are some examples of the absent-minded professor trope from movies, from television shows, and so on. Because all of these tropes are examples from media that people consume for entertainment, there's a concept of a spoiler. And so a spoiler is a piece of information that tells you something about what's going to happen in the plot of the movie, the TV show, or the book that would somehow impair your enjoyment. Examples of spoilers include plot twists, surprises, that sort of thing. So here we have some examples of spoilers and things that are not spoilers from TV tropes. And so as you can see on the spoiler side, critical plot points like Luke destroying the Death Star, the destruction of the planet Alderaan, the death of Luke's family, these are all spoilers because these are critical plot points that are often a surprise. Events that are less consequential to the plot are not considered spoilers, such as the banter between Luke and Leia, oblique mentions of the Death Star doing quote-unquote evil things, not explicitly mentioning blowing up planets, or a firefight in a garbage chute. One of the interesting things about TV tropes is that people who write these trope examples have annotated whether each example is a spoiler or not. So we can use this to build a classifier. What we do is we download all of the pages associated with a particular television show. We're just concentrating on television shows here. Gather all of the complete sentences and split those into spoilers and those without spoilers, where 50% of the sentences are spoilers and 50% of the sentences are not. We then create training, development, and test data sets. This is important because we're going to be developing new features, and we want to see how well we do on the development data, but we only test on the test data at the very end after we've figured out all of our features. If we didn't do this, we might end up overfitting, creating features that are just good for a particular data set. This is why we have the test data set in reserve until the very end. I'll show results using the support vector machine classifier, but you get similar results with other classifiers as well. So let's talk about how various features do at predicting whether a particular sentence is a spoiler or not. The first feature that we can do is we can create a feature for every word in the sentence. So if we have a sentence that has the text, "These aren't the droids you're looking for," we can make a feature out of every word in the sentence. And so this gives us an accuracy that's only slightly better than chance. So remember, the chance baseline of guessing is 0.5. So we're only doing slightly better than that. This is called unigram features. And think about what these features mean. If we create features that look like this, we lose all of the word order meaning in the sentence. So remember, a support vector machine just treats every input as a vector in some high-dimensional space. There's no notion of ordering to those vectors like there is in English sentences. But there's also a more obvious problem here. We're differentiating these when it's capitalized with these when it's not. And we're also differentiating plurals from singular words. So droids and droid are mapped to different features. And so this creates an explosion of features and perhaps hurts the accuracy of our classifier. The next thing that we'll do is try to correct these errors. We will do what's called normalization. We'll lowercase everything, and we'll get rid of endings of words, which should hopefully allow us to map droids and droid to the same feature. So if we do this, we get a slightly different feature vector. All the words are lowercase, and we get rid of droids. That now becomes droid. And our accuracy increases slightly because of it. Another thing that you might notice is that we're including a lot of words that probably don't matter when it's a feature or not. So words like the and for probably are not going to help us tell whether a particular piece of text is a spoiler or not. So we use what's called a stop list and remove all of the features that appear in more than 10% of the observations. So if we have the input, these aren't the droids you're looking for, really the only content words in that sentence are droid and look. And if we remove those, our accuracy creeps up slightly. But remember how I said that we're removing all order to the sentence. And that's still happening. How can we get back some notion of word order? What we can do is, instead of having what's called unigram features, we can have bigram features. So for every pair of consecutive words, we create a feature. So if we see these are in our sentence, we add a feature, these underscore are. So this creates a lot of features, but hopefully we'll be able to gain from it by being able to detect when a particular sentence is a spoiler or not. So if we have the sentence, these aren't the droids you're looking for, we get a bunch of features for all of these bigrams. And again, our accuracy creeps up. But we can still take advantage of pruning. We can remove the features that aren't going to help us much and concentrate our attention on the ones that will. This is a good idea because not all bigrams appear often, and if we remove the infrequent ones, and we remove the ones that aren't going to help us because they're so frequent, we can help our machine learning algorithms find better answers. So if we have the input sentence, these aren't the droids you're looking for, and we prune the useless features, we get an example that looks like this. And so now our accuracy goes up again. So this starts the process. So how do we go beyond this to discover new features that would help us? So what you do is you build a classifier, and then you make predictions on your development set. And then you start inspecting where you went wrong. Look at the contingency, see which cells are contributing to you not getting good results. This is called error analysis. And think about, for each example of an error, are there features that could help you discover a lot of these problems and get them right? Are there features that are confusing the classifier? Are there features that are never appearing in the development set? If so, that feature isn't useful. Try to think about pervasive patterns that appear in your errors to help you figure out what features might be useful. This is very similar to what we did for regression. So remember, in regression, the way that you build up new inputs to your regression is to look at the residuals and look for patterns. We're doing exactly the same here, but instead of looking at a plot of residuals, we're looking at errors that the classifier made, so discrete versus continuous. Make a table where you have the number of positive examples with that feature, the number of positive examples without that feature, the number of negative examples with that feature, the number of negative examples without that feature, and then see, are there patterns in that table? If so, that might be a good feature you can include. And this is what you'll be doing in homework number 3. I've given you a bunch of Quizable questions where you have both a partial example of the question text and a guess of what the answer could be. And these guesses are Wikipedia pages. And your job is to say whether that guess is correct or not. I've also provided you test data where you don't know if the page is correct or not. At the moment, I've given you a small number of features. Using these features should get you to around 81% accuracy. And for these features, it doesn't matter much which classifier you use. The most important part is adding additional features. I encourage you to go out, find new data, and extract useful features from these data. Last year, we had a similar competition, and 2 of the students in the class, Kim Glasgow and Jackie Zajac, came up with some really good ideas for features that we could use for the spoiler detection task, and we ended up writing a paper about it that was presented at a conference. And I'm really hoping that we can do similar things this year. So please work hard on the Kaggle competition and try to come up with some interesting features.